All right, so Unit 3. Okay, we're going to be talking about circular motion in Unit 3. So today will mostly be just the principles behind circular motion. Okay, what makes circular motion happen, what it looks like, what it is, okay, things like that. In the simplest sense, circular motion is when something moves in a circle. Shocking. Okay, yeah. Okay, but what makes something move in a circle? Okay, actually it's a combination of both of those things. Okay, if something is moving in a circle, like this right now is moving in a circle at a constant speed. Is it moving at a constant velocity? Why not? Oh no, it's not moving down, it's moving in a circle. Its direction is always changing, right? If you're moving in a circle, aren't you always turning? Okay, in order to turn, there has to be a what? A change in velocity and thus a force. Okay, so there's always a force that's causing something to move in a circle because that's the only way you get a change in velocity to occur. Now, the source of the force in this example is obvious. It's the string. Okay, the tension in the string. Which way is the string always pulling? Towards the center. Okay? In order for something to move in a circle, it must not only be accelerating towards the center, but it must also be being pulled towards the center by a net force in that direction. Okay? Everybody with me there? Okay. So we're going to look at, again, what circular motion is, how it happens, okay, and understand the relationship between period, okay, which is going to be a new term, okay, and centripetal velocity. So period is the time it takes for one cycle. Okay, or in this case, one circle. Right? How long it takes to make one complete revolution is the period. So the period of Earth's orbit around the sun is how long? 365.25 days. That's why we have a leap year every 4 years. You got to make up for that extra quarter of a day. Okay? So 365 and a quarter days is the period of Earth's orbit. Okay? The period of Earth's rotation is 24 hours. Okay, the time it takes for one cycle is the period. Okay, so period is, right, we might just want to write this, time for one cycle. And I got to reorient the board. Okay, so frequency tells us the number of cycles per second. Period tells us the number of seconds per cycle. Okay, they're the inverse of each other. Okay, they're comparing similar things, but they're just doing it from opposite ends of the spectrum. Okay, so uniform circular motion is the motion of an object traveling at a constant speed, okay, along a circular path. So constant speed, but an ever-changing velocity, okay, and thus direction. Okay, so in the figure at left here, the speed of the plane is the magnitude, so the length of this arrow, okay, but the arrow is obviously always pointing in a different direction. So velocity is changing even though speed is not, and any change in velocity requires an acceleration, which requires a force. All right, so those are the principles of uniform circular motion. Something can travel at a constant speed, but it is always accelerating towards the center of the circle because of a force pulling it that way. All right. Now, sometimes the force isn't quite as obvious. Right? Anyone ever ridden the Gravitron at the Calgary Stampede? It's the one that spins around, and then you're kind of pinned to the wall, and the floor falls away, but you don't fall. Okay, you're moving in a circle. What's pushing you towards the center? The wall. Why is the wall pushing on you? Right, because you're pushing on it because of Newton's first law. Okay, what do you want to do? Once you get moving, Newton's first law says that you naturally want to keep going in the same direction, in a straight line, right? But when you're on the gravitron, the wall prevents that, and it keeps pushing you back towards the center, making you move in a circle. When it gets going fast enough, your inertia is so big that you push so hard against the wall, and the wall pushes hard so back that you get pinned to it, and you can't fall. Okay? Giving you a feeling of apparent weightlessness. Okay? You don't fall, but you're being pushed back towards the center because of your inertia. Okay? All right, so that sort of makes sense? The idea there, kid? It would be really hard. It'd be like being on a merry-go-round, which you guys probably don't have any experience with because they've been deemed unsafe and no playgrounds have them except for those enclosed teepee-looking ones. Okay. It only takes one person to lose a finger and ruin it for everybody. Okay. Yeah. See, when I was a kid, we had these things called merry-go-rounds. I'm actually going to show you a video of people who are responsible for eliminating them because they're stupid. Oh, it's good. Believe me, it's good. It's really funny, actually. It is a lot of people getting hurt, but it's, their own stupidity. So it's like fail Army funny. Yeah? Okay. All right. So what we're talking about here, guys, is that you have this inertia. Your inertia wants you to go in a straight line, but to go in a circle, okay, requires someone to pull on you or something to pull on you or something to push on you towards the center. Now, if you're moving really, really fast around and around in a circle, it's not just your body that wants to go, it's all parts of your body that want to go in a straight line, including your blood. So if you're doing that, okay, what might happen to the blood in your head? It might leave your head, which would cause you to? Yeah, to black out. Okay, that's what happens to fighter pilots when they do the centrifuge. When they take high G turns, they sometimes black out, okay, because the blood in their body becomes so heavy that their heart can't pump it to their brain. Okay? And as a result, their brain becomes oxygen starved and they black out. Okay? It's why they have a lot of training, first off, and they also have a special suit. If you've ever seen like a fighter pilot's flight suit, it's like one big blood pressure cuff. Okay? You guys ever had your blood pressure taken? Okay, so imagine that is over your whole body. So when they start pulling high G's in their aircraft, the computer in their plane will start inflating different parts of their suit, and it squeezes the blood back into the center of their body and towards their head to allow them to stay conscious for another second, 2 seconds, whatever. The difference between being shot down and crashing, okay, or being successful and making a turn. So they have these suits that help to keep the blood in. They also they do this grunting thing where they are using the muscles in their neck to squeeze against their carotid artery. Okay, so if you've ever watched any like gun camera footage of like fighter pilots taking a dive and then pulling out of it, you'll often hear them making this like sound, and it's what they're doing is they're squeezing their carotid artery with the muscles in their neck, forcing the blood back up, okay, and into their head. Okay? It's also why if you ever meet a fighter pilot, just look at their neck. They have gigantic necks. And I don't mean long, I mean muscular. Okay? You imagine you're wearing not just your head, but also this big heavy helmet that can be like 15-pound helmet, okay? And you're pulling a turn where you're pulling 4 or 5 G's. So now you've got your helmet weighing 5 times more than normal, and you've got to be looking over your shoulder and turning around and looking around to see who's shooting at you. Okay, you get really strong neck muscles in a hurry. Okay, trying to move all that weight around. Okay. All right, so I'm going to show you the funny video now because I just can't wait anymore. It's too funny. Okay, so looking here then, guys, at the formula for centripetal velocity. Okay, so sometimes we need to be able to calculate how fast something is moving as it travels in a circle, right? So normally, if we're talking about something moving at a constant speed, okay, we use speed equals distance over time. But now we're talking about something that's moving in a circle. So what do we call the distance around a circle? How do we calculate that? So no, not squared. Pi times d, or pi times, yeah, how much of the radius? 2 times, right? Okay, if it's pi times diameter, it's pi times the distance across. If it's radius, it's 2, okay? And we always use radius in physics. So really what we're saying here is this formula is v equals d over t for a circle, right? So we calculate the circumference, 2 pi r, and then divide it by the period, the time for one rotation. Okay, everybody with me on that formula? So it's really just v equals d over t. Now, the other thing we need to realize is that period and frequency, which we talked about right at the beginning, are related this way, right? Because we said frequency is cycles per second, but period is seconds per cycle. right? Which means they're the inverse of each other. So if I want to calculate period, I go 1 over f. Okay, if I want to calculate frequency, it's 1 over t. Okay, so 2 new formulas here that we'll be using in this unit. Now, if I'm looking at this formula here, where I've got speed equals 2 times pi times r, and then I'm dividing by t, is that the same as doing this? 2 times pi times r times 1 over t. Is that the same thing? And what's 1 over t equal? Frequency. So we could also have this formula be 2 times pi times r times the frequency. Right? There's more than one way to calculate it because frequency and period are the inverse of each other. So I can either go 2 pi r and divide by t, or I can go 2 times pi times r and multiply by frequency. Same thing. Okay. Okay. Questions on that? All right. So, example. Example is being done a lot right now. Okay. The nice thing about this unit is I'm usually teaching it first semester when everyone's getting their winter tires put on, and I'm teaching it second semester when everybody's getting them taken off. Like me yesterday. That was smart. I'm gonna get 4 centimeters of snow the day after I get my winter tires taken off. Anyway, okay, when you put tires on a rim, you have to balance them. Anybody know why? Yeah, your car will shake all the time because a tire, even though it looks fairly uniform when you look at it, it's not. Okay, a tire when it's formed is essentially formed by pouring liquid rubber into a mold and then allowing it to cool. That doesn't necessarily distribute the rubber evenly. And as you use a tire, okay, you may wear different parts of it differently, and so it'll become out of balance. What can happen then is that as you're driving at higher speeds, there's more weight on one side of the tire than the other, and the tire will start to chatter. It'll start to oscillate, okay, and shake. Anyone ever been in a car where that happens? Okay, it just happens sometimes, and you just have to get the tire balanced. Okay, it can even happen if you drive through a bunch of deep snow and then go on the highway. Okay, if snow is collected on one side of the rim and not on the other, your car will shake when you get up to highway speed because there's more weight on one side of the wheel than the other. Okay, so what we have to do is put little weights on the inside of the wheel in order to make sure that the weight is distributed evenly throughout the wheel, and then your tire and your car will run more smoothly. Okay, it's actually very bad for your car to have it do that because it can wear out a lot of the suspension components. Okay. So what they do is they put the tire and the wheel on this machine that basically just spins it. Okay, and the machine is on a spring. Okay, so this part right here is on a spring that can move up and down or back and forth. And the machine just detects what kind of movements the tire and wheel are making as they spin the wheel around. Okay, and then it stops the wheel and it says here, here, and here put a weight and put this much weight. Right? And then they balance your tire by doing that. So if you've ever looked on more modern wheels, they're usually just stuck on. They're like a little square and they're stuck on the inside of the rim. Sometimes on older wheels, there'll be a tab, okay, that'll kind of be tucked underneath, and there'll be a weight here, and it'll be tucked underneath the tire against the edge of the rim. Depends on what kind of rim you have. Okay, but this is using the principles of circular motion in order to make our cars safer, because it's not safe to have a car that shakes like crazy when you're driving at high speed. Okay. All right, so we're going to look at this one as an example of using this formula. Okay, V equals 2 pi r over t, or 2 pi r times frequency. Okay, so a wheel of a car has a radius of 0.29 meters and it's being rotated at 830 revolutions per minute. Now, we probably don't want it in per minute, we probably want it in per second. Okay, so what would I need to divide that by? 60. Okay, if I divide that by 60, then I'll have how many rotations per second. Okay, we don't use revolutions per minute for anything other than engine speed. Okay, so 830 revolutions per minute, so we'll divide that by 60. So this thing is spinning the tire so that it rotates 13.8 times every second. Okay, it's pretty fast. Okay, your tire is rotating really fast. So 13.83 will be our frequency. What do we call a rotation per second? Anyone know or a cycle per second? What's the name for that? Use it in music all the time. You measure musical frequencies and notes in hertz. Yeah. Okay. A hertz is a cycle per second. Okay. If it's a tuning fork, it's the number of times the tuning fork oscillates back and forth in 1 second. If it's the frequency of the tuning fork. Okay. So in this case, it's the frequency of the tire going around and around on the machine. Okay. So we got radius, we got frequency. Can we calculate the speed? Yes. All right. So we're just going to go V equals 2 times pi times 13.83. Okay. Times, sorry, the radius, which was 0.29. I need to leave myself enough room. Okay, so we got 2, and should I use 3.14 or should I use the pi button? Pi button, yeah. Okay, times 0.29, so there's my radius, times the answer from the previous one there. Okay, so this tire is moving at 25 meters per second. Okay, whoop, not divided by 3.6. Okay, that means 90.72 meters per kilometers per hour. Right, so they spin that thing at about 90 kilometers an hour, okay, in order to see, and they don't just like whip it up to 90. They slowly increase to see where it chatters. Okay, and usually if you have an unbalanced tire, it chatters at several different speeds. Okay, it'll chatter at like 40, and again at 80, and then again at 120. Right, they're called fundamental, and then sorry, it's the first one is the fundamental frequency, and then you've got your resonant frequencies after that. Okay, and they're all just multiples of the first. Well, but they would have passed one of the previous speeds where it would chatter as well, right? Okay, following how that formula works? Okay, other way I could have done that, I could have gone 1 over this and found the period, and then used period in 2 pi r over t. But there was no point in doing that if I had a formula that already used f. Okay. All right, so that's what we just did, so we'll skip over that. All right, so definition of uniform circular motion emphasizes that the magnitude of the velocity vector is constant. That means it's moving at a constant speed. Okay, so it's not going faster or slower. But what is changing is the direction. And in order to turn something, you need to have a force that's causing it to accelerate. That is to change direction and change velocity. Okay? So any change in velocity, okay, even if it's only a change in direction, means that an acceleration is occurring. Right? So when something is moving around and around in a circle, there is a centripetal acceleration. Right? How many people think that word sounds close to the one I should have used, but it's not quite right? I said centripetal. How many of you are thinking centrifugal? Okay, so differences. Centripetal means center seeking. Okay. The thing that makes something move in a circle is pulling it towards the center. So it's centripetal, center seeking. The term centrifugal or centrifugal means center fleeing. And a lot of times people will use this term incorrectly, and they'll say something like, oh, that's because of centrifugal force. Okay, there's no such thing as centrifugal force. There's no force trying to pull something out of a circle. Okay, the only thing that makes you want to leave a circle is your what? Inertia. And that's not a force. That's just your tendency to want to go in a straight line. In order to stop it, I have to exert a force that pulls you back towards the center. Everybody follow me there? So there really isn't anything, there's no such thing as centrifugal force. Okay, there's inertia, but there's no centrifugal force. The desire to leave a circle is not a force, it's just inertia.
So like on the line, sorry, when you're talking about
the gravitron, yeah.
Yes. The force you're exerting on the wall is centrifugal.
No, it's actually tangent. Okay, so here's the gravitron. I'm going to draw it like you're standing on it, because actually if it was going, I don't know what happened to you there. You got your knee up here. Okay, so you're standing on this and it's spinning around and around. Your inertia wants you to go this way. Because this is always turning, you're pushing against it because of your inertia. Okay, so then the surface, which can only push because of normal force straight away from itself, doesn't matter where you are on the circle, that force is always pushing directly towards the middle because it's always perpendicular to what you're standing or pushing on. Okay, but there's no force that's trying to pull you out of the circle. Yeah, I mean there's some situations where there could be a force that's trying to pull somebody out of a circle, but it's pretty rare. Right? There's usually just inertia trying to make you go in a tangent. Okay? Now, we have a biblical story that uses this same idea. Anybody know what it is? Nope, not Moses. David and Goliath. Yeah, totally. How did David kill Goliath? With a sling, not a slingshot. Okay, he's not Parkinson. Okay, he didn't have one of these that he pulls it. He had a sling. A sling works a lot differently than a slingshot. So a sling is just a piece of, it's just a strap. It could be leather, or the one he would have used would have been made out of hemp. It would have been braided from hemp. So he would have had the rock in it, and he'd be swinging it around and around and around. Okay, in order to let the rock go, you have to let go of one end of the sling. And when you do that, the sling just pops, and then the force that's holding the rock in is gone. Okay? And then the rock travels in a straight line from the point of release. So if my target is over here, I need to release the rock when it's over there. Okay? You'd have to be pretty highly skilled in order to have any accuracy with one of these. If anyone's got one of those things that you can use to throw a ball for your dog, okay, it's like a sling too. You can go like this, and then you let it go, and you can throw the ball really far, way farther than you can with just your hand, because you're using a longer what? Yeah, so like a longer lever, right? Like I can only throw so fast with my arm, okay? But if I have a longer arm, I can throw faster, okay? Just got a longer radius, right? Longer lever over which to exert the force, right? So a sling essentially allows you to multiply your force by making your arm longer and allowing you to rotate that thing at a much higher rate of speed than just your hand could do, right? So you suppose that's believable? That someone could kill somebody with a rock out of a sling? Okay, all right. So there you go. Okay, possible. Okay, we've seen it now. They hit the load cell. Okay. It's just like when you faint, when you pass out, you go forward. It's just the way your weight is. So you would have got hit, head would have snapped back, hips would have gone forward. Yeah. I would say probably somewhere in the neighborhood of 200 meters per second, something like that. Yeah. Would have been fast. I mean, the end of the sling was going more than 300. Okay, it would have to be going close to that. Yep. All right, so we calculate centripetal acceleration, which is the acceleration back towards the center. Okay, we take v squared, so whatever the speed is, okay, and divide it by r. All right, so that'll give us our units for acceleration. Remember, this is going to be meters squared per second squared. Okay, when we're taking speed squared and we're dividing that by meters, right? So the meters cancel and we're left with meters per second squared, the units for acceleration. It's not a formula we use very often, but it leads us into centripetal force, okay, which is what we're going to talk about on Wednesday, because obviously Monday we're doing our conservation of energy lab. Okay, everyone with me on that? Well, it's always the same direction. It's centripetal. So it's always where? Always towards the center, right? In fact, in this unit, we very rarely write the vectors on it because anything centripetal, the vector is a given, right? It's always towards the center. Centripetal force towards the center, centripetal acceleration towards the center, okay? Unless a question specifically says what's the magnitude and direction of the centripetal force, you don't even bother writing it. Centripetal says towards the center, okay? Does everyone kind of follow me on that? Okay, so yeah, the vector analysis part of this is quite a bit easier. It's towards the center, always. Okay? It has to be, otherwise the object's not moving in a circle, right? The velocity, always tangent to the circle, right? Everyone remembers what tangent is, right? Okay, a line that touches a curve but doesn't cross it, right? So in any case, anything moving around and around in a circle, its velocity vector is always tangent to the circle at that point, okay? And that's the direction it would go were it released, okay? And I had this happen to me one time doing a demo for vertical circular motion in this classroom. I had a pail full of water, okay? And I was showing people that the water doesn't come out if I rotate it like this, okay? But the handle broke, okay? And where does the handle break? Right here, because that's where the most force is put on it. Right at the top, gravity's pulling down, I'm pulling down. There's hardly anything there. Okay, but at the bottom, gravity's pulling down, I'm pulling up, and that's where the most force on the handle is. So as you're coming around, that's where it breaks, and then it goes. And I was standing right here, and I went like this, and it went. It went right over the kid who was sitting in Curtis's desk, and it hit the wall. No, the bucket didn't. He got wet, but the bucket didn't hit him. Yeah, it's kind of scary. I have not done that demo since because they just don't make ice cream pails the way they used to. Okay? It's crummy plastic handles.
What about you checking the knot there?
Yes, I checked the knot several times because I actually put a different roll of tape on here. So I had to make sure it wasn't going to come off. This one wouldn't hurt so bad. Okay, so everyone gets the idea here of a centripetal acceleration? Yep. Yes. Well, the water's trying to get out, right? You're swirling it around, and the water's trying to go in a straight line, but the inside of the water bottle prevents it. Then the inertia builds up. It just keeps moving. When you stop, it's going to keep moving for a little while until the friction against the side slows it down enough that it stops. Yeah. Okay, so centripetal acceleration, remember, like we said, vector quantity, the direction's always the same, always towards the center of the circle, including for things like the moon orbiting the Earth. What's acting as the centripetal force there? Gravity. Gravity pulls it towards the center of the Earth. Okay, now it's not as simple as that because the moon also pulls on the Earth. Okay, they actually kind of wobble around a common gravitational center that is actually right about here, just slightly below the Earth's surface. Okay, is the gravitational true center of the Earth and the moon. So the Earth wobbles back and forth as it goes around the sun. It's not a perfect circle. It actually goes like this as it goes around the sun because the moon pulls on it, okay, a little bit too. All right, we will leave it at that. Okay, and on Monday we're doing our conservation of energy lab. So make sure you got the SparkView app ready to go on your phone for Monday. Okay.